Hey guys, so this is implicit differentiation, and if you are following along with our sections in the textbook, it is section 2.5. So just as a forewarning, this is going to seem maybe a bit strange at first, and admittedly, this video is designed to introduce the topic of implicit differentiation and go over exactly how you differentiate implicitly. So again, I'm going to explain all of that, what that means, but I guess what I'm telling you is the application of this or why we're doing this is going to come just a little bit more down the road. Okay, so we are learning a little bit of base knowledge here, and then we're going to apply that base knowledge in just a little bit. Okay, so I guess I'm asking you to keep an open mind throughout this video. Try and follow along the best that you can, and as always, jot down any notes and questions that you have so that we can talk about them a little bit further later on. Okay, so let's get going. Before we understand what it means to implicitly differentiate something or use implicit differentiation, we need to know what it means to have an implicit function, right? So we know how to take derivatives of functions. We've been doing that for the past couple of weeks. But in order to differentiate implicitly, I need to have a grasp on what it means for a function to be implicit. Okay, so I'm actually going to start with the opposite of implicit, which is explicit. And an explicit function is actually something that you've been using your entire math career. This probably wasn't described in that way, or that those words weren't used when talking about the function you're using. And so what that means is an explicit function is a function where everything is told to you. So you know everything about that function. And by that, I mean, you know that it's labeled either y or f of x, and you know that that value, y or f of x, is equal to x squared or sine x or e to the x or whatever the function may be. Everything there is right in front of you, right? So, and I know that seems kind of strange, but like, well, yeah, of course. How else would I use an input to get an output, and so on and so forth? But there are such things in math that come up, which are called implicit functions. And basically, all that means is that there is some function that exists. So you're told some function exists. And typically, you're also told what the label or the name of that function is, whether it's y or f of x. For this particular video, will almost always just be y. But so you know some function y exists. What you don't know is anything else about that function. So you don't know what the operation that is being done to the input is, right? So I don't know that x is being squared. I don't know that I'm taking the sine of x, or that the the exponential function is being used for x, e to the x. All I know is that there's some function y, and it could be any number of those different types of functions that we've worked with. Right? That is an implicitly defined function. It is just, hey, here's a function f of x, here's a function y, it exists. Its variable, right? So its input or its independent variable is x. That will most likely always be told to you, or whatever the independent variable is. But we just don't know exactly what the function is itself. Okay, so anything or anytime you just see a function or an equation that is labeled as y or f of x or just y by itself, we're using implicit functions, and eventually we'll use implicit differentiation. Okay, so we are going to eventually take implicit functions such as y, or something being acted upon y, and use them as part of bigger overall explicit functions, or they're going to be composed with other explicit functions. And so I'm going to kind of slow down here just a second, because I know I'm using a lot of the same words, and this is probably a bit confusing. So the next slide is going to tell you or give you an idea of how they'll look, right, and how we'll see them. So here are two different examples of implicitly defined functions and equations. So that first one I want you to focus on, right? Y plus e to the x plus sine of y equals 5. Okay, well, there's some elements there that are very familiar to you, right? I've seen equations with y in it. I've seen equations or functions themselves with e to the x. I recognize there's a sine function, and then 5 is a constant, which, again, is something that you've dealt with plenty of times in your math career. However, this is definitely different, right? Because I haven't necessarily added something to y, and then I certainly probably haven't taken the sign of y. And why does that equal 5? And how do I deal with this? What am I doing this for? This is, at least on the left side of this equation, is an implicitly defined function. Because, yes, I know that e to the x is here. However, this y value, well, what is y equal to? Right? What is the function y that I'm using that I could potentially replace here in terms of x to have a full function in terms of x? I don't know. I'm just told that it is y. And then additionally, well, now I'm taking the sine of y. Again, I don't know what y is equal to. Is y equal to tangent? Is y equal to x squared? Is y equal to, the square root of x? I don't know. I just know that the sine function is being acted upon y. And that whole crazy thing equals 5. All right. And then down here, this is just another version, right? So these are just two examples of implicitly defined functions and an implicitly defined equation. So the first part, xy plus x to the fifth. Okay, I know how to work with x as a fifth. I've got x multiplied by y, and then on the right-hand side of the equation, it's cosine of x divided by y. I know it's implicitly defined because there's an extra y value in there that is being a part of an operation, right? So in both examples, y is no longer just the label of the function. It's actually a part of the overall operation of the equation or the function itself. Right? It's no longer just cosine of x, it's cosine of x divided by y. It's x multiplied by y. And so as soon as that happens, we know that we have an implicitly defined function and an implicitly defined equation. Okay, so now we have a little bit of a background on what an implicit function is. And so now we're going to try to work with, well, how do we differentiate an implicit function? And again, I don't necessarily for today want you to think so far into the future of, well, once I find the derivative, what does that mean? We will get to that. I promise you, we'll use this in application. But for right now, I just want to focus on the technique and the strategies of finding the derivative of an implicit function. And so I'm going to start with the very easiest one, which is just y itself. Okay. So if I just put y on the page and I say, find the derivative of y, how do we do that? Well, again, y is some function. It could be e to the x, it could be sine, it could be tangent, it could be all these different things. And if I knew what that was, I could use one of the rules that we have and say, well, here's the derivative, f prime equals blank. But I don't know what it is. I just know I have y. And we're going to use some very familiar notation here. And so what I would say is that if y is a function of x, okay, so I know it's a function of x, I just don't know what the exact function is, its derivative with respect to x is equal to dy dx. And that's all I'm going to label it as. The derivative of y is equal to dy dx. So what that tells me is every time I encounter a y within an equation or in a function that I'm differentiating, dy dx is its derivative. Okay, so if it's y plus x, the derivative of that expression is the derivative of y, which is dy dx, plus 1, which is the derivative of x. Very simple example, and we're going to get into a couple of other ones here, but just that idea. Every time we see a y, its derivative is dy dx, and that's how we're going to keep it. We're going to label it that way. All right, so dy dx, please keep that in mind. So let's jump into an example, all right? And I'm actually going to sort of mix and match here a little bit. If we add y into a function that has other pieces and we want to find its derivative, specifically with respect to x, basically what I'm trying to say there is, well, all right, I have this equation. I want to find dy dx. I know that there's a function that lives here. I know y is defined as a certain function. And so I want to find its derivative, dy dx. And so here's my first example. Y plus x squared equals 5 sine x. If I were to take the derivative of this entire equation, we know that if we do something to one side of the equation, we have to do it to the other, right? It has to be equal. If I subtract 1 from one side of the equation, I have to subtract 1 from the other. If I multiply by 2 on one side of the equation, I have to multiply by 2 on the other side. This works exactly the same for differentiating an equation. If I differentiate y plus x squared, I have to then differentiate 5 sine x. And I have to differentiate them with respect to the exact same variable. So if I were to take the derivative of this entire equation, what happens? Well, on the left-hand side, the derivative of y is dy dx. We just talked about that, right? Y to the first, its derivative with respect to x is dy dx. I don't know what the exact equation is just yet, but I know that its derivative is labeled as dy dx. So that's what I'm going to use that. I then move forward to x squared. Okay, well, x squared is actually the same variable that I'm differentiating with respect to, right? This is a really important piece. I'm differentiating with respect to x. Therefore, when I get to x squared, I'm going to use the same exact differentiation techniques that I've been doing for weeks now. There's no y involved within x squared. Therefore, I can just use the same rule. The derivative of x squared is 2x. On the right-hand side, same thing. The derivative of 5 sine x. That looks like something we've been doing a lot of, and it is because, again, you don't see a y there. That is an explicit function, 5 sine x. Differentiate that, we get 5 cosine x. The next piece to this is just solving for dy dx, and this is going to be a very similar process that you see throughout each example. How do I solve for dy dx? I subtract 2x over. And so the overall derivative for this function is 5 cosine x minus 2 sine x. That's what dy dx equals. And so, yes, if you're looking at this example and you're saying, well, couldn't I have just subtracted the x squared over in the beginning and then just taken the derivative? And I would have gotten the same answer. And the answer to that question is yes, absolutely. You could have done that. However, there are going to be times, and we'll see in just the next example, where that's not always possible. So I wanted to show you just a quick and easy example of how implicit differentiation works and what are the strategies and techniques that we're going to use. So in general, what did we do? Well, we looked at both sides of the equation separately, and we took the derivative with respect to x of each individual piece. So we took the derivative of y, we got dy dx. We took the derivative of x squared, we got 2x. Derivative of 5 sine x is 5 cosine x. And then I solved for dy dx. That is going to be our process and our thought strand throughout this entire unit. Let's look at another example. We're going to bump it up just a little bit, right? So let's say if I have the equation y squared plus 5x equals sine y. Now let's find dy dx. So hopefully you're looking at that equation and you're saying, okay, well that is definitely different, right? Y squared plus 5x equals sine y. There's a couple of different pieces there because now I have a y on both sides of the equation. I can't solve for just y itself and take the derivative like normal. And so this is where implicit differentiation is really going to come in handy. And here is the big idea of the whole video. If we can commit to saying that y is some implicit function that we don't know, so y equals something in terms of x, but I don't know it. But I'm taking that function and I'm doing other things to it. So specifically for this one, I'm squaring y and I'm taking the sine of y. Well, what's happening there is I'm taking a function y and I'm putting it inside of another function, in this case x squared and sine of x. That creates a composition function. And we know that with any composition function, I have to use the chain rule. And so the two pieces that I have right here, this isn't the overall problem, right? The overall answer, but this is just breaking it up a little bit. So the difficult parts here are the y squared and the sine y. 5x we can deal with no new information. So I'm going to leave that alone for just now. But for y squared, let's look at how to take its derivative. If I interpret y squared as f of g of x, where the outside function is x squared and the inside function is y, and then enact the chain rule, what comes out? Well, the chain rule says use the power rule on y. So I'll bring down the 2, subtract its exponent to get to 2y. But then I need to take the derivative of the inside. Well, the inside function in this case is just y itself. And so the g prime part of this is dy dx. And so the derivative of just y squared with respect to x is equal to 2y multiplied by dy dx. Move over to sine y. Exact same idea, right? I'm going to use sine y as a composite function where sine of x is the outside function and y is the inside function. The derivative of sine is cosine. I'll keep my original input, which was y. but then I'll multiply by the derivative of the input and get dy dx as that g prime of x piece. So the derivative with respect to x of sine y is cosine y multiplied by dy dx. Let's put these pieces together, right? Because these are just two individual pieces of the overall equation that I have up there. So here's the original function. If I'm trying to find dy dx, what are my steps? Well, the first piece is I need to take the derivative of y squared. We just did that, right? Bring down your 2y, multiplied by the derivative of the inside, which is dy dx, plus the derivative of 5x with respect to x, which is just 5, equals the derivative of sine y. Well, sine goes to cosine, keep your original input y, but then multiply by its derivative, which is dy dx. If we're trying to find dy dx, notice that we have two dy dx's here. And this is going to be another common pattern. We are most likely going to have multiple dy dx's within any one equation. In order to find dy dx, at this point, it's actually all algebra, because in order to solve for dy dx, I need to get all of dy dx's on the same exact side of the equation and get rid of all the other pieces that are involved. Bring them over to the other side of the equation. So how would I continue to solve this problem? So we're actually done differentiating. We're done the calculus piece. If you're good up to here, you're doing really well, all right? Because we're done with the calculus piece. And now this is just more algebra, actually. So what would my next step look like? Well, if I want to combine like terms, and at this point, like terms is anything that has a dy dx attached to it. So I'm going to subtract cosine y dy dx over to the left-hand side, and I'm going to subtract the 5 over to the right-hand side. Everything with dy dx on the left, everything without a dy dx on the right. Now, again, I just want dy dx by itself. I want to solve for dy dx. Since both pieces, both terms on the left-hand side have a dy dx, I'm allowed to factor a dy dx out of that part of the equation. And what's left inside of that quantity now is 2y minus cosine of y. All right. Imagine if you wanted to work backwards here just to get this, right? If you distributed this dy dx back in, you would end up back at this line right here. Okay, so all I did was factor a dy dx out in order to get a singular dy dx that I can solve for. How do I solve for dy dx at this point? It's being multiplied by 2y minus cosine y. So of course I will divide both sides by 2y minus cosine y to get a final answer of dy dx equals negative 5 divided by 2y minus cosine y. Very common pattern. You're going to use implicit differentiation on the pieces that you have. Combine your like terms once you have all of your dy dx pieces over to one side. Factor a dy dx out, and then divide by whatever is left over. All right, my third and last example for this opening of implicit differentiation. Here's my expression, my equation rather. I want to find dy dx. Okay, so now this one, again, bump up the heat just a little bit. What are all the different things that we're going to have to do? I notice that cosine has an x multiplied by y within it. So that is going to use implicit differentiation. As soon as I see a y mixed within a cosine and also being multiplied by x, that's my cue for implicit differentiation. 10x squared is not going to use implicit differentiation. 3x is not going to use implicit differentiation. I'm going to use my normal strategies on them. All right, so let's take it step by step. My first step would be to take the derivative of cosine of xy. Now follow along here, right? Because there's a couple of different spots or a couple of different pieces and rules that we're going to use. The cosine of xy is a composite function in itself. It's no longer just the cosine of x or the cosine of y. It's the cosine of x multiplied by y. So the first thing I'll do is take the derivative of cosine, which is negative sine, and keep its original input, xy. I then, using the chain rule, have to take the derivative of x multiplied by y. Well, if I take the derivative of x multiplied by y, I have to use the product rule. So the product rule says to take the derivative of x, which is equal to 1, and multiply it by the second piece, which is just y by itself. Then take the derivative of the second part, which is y, so I get the dy dx, and multiply it by the first part, which is just x. So the derivative of the product x multiplied by y, using both the product rule and implicit differentiation for the y piece is y plus x dy dx. The derivative of 10x squared is just 20x, and the derivative of 3x is just 3. Okay, so now I have to work towards getting dy dx by itself. How do I do that? Well, I can easily enough subtract the 20x over, because that doesn't have a dy dx. So I'm going to move that over to the right-hand side. So we'll subtract the 20x over to the right-hand side. That's not a problem. But if I notice, this dy dx is trapped inside of these parentheses. I can't just move this dy dx out or anything, because it's inside of that quantity, right? And additionally, this quantity is being multiplied by negative sine xy. I can't, excuse me. Well, there are a couple of ways, I guess I should say, to attack this, right? Because since this is being multiplied, we could divide negative sine of xy over to both sides after I subtract 20x. Or I could also distribute the negative sine of xy into these parentheses. And when I do that, what I've done is I've created very distinct terms, right? I've got a negative y sine of xy from that first piece, a negative x sine of xy, dy dx, and then on the right-hand side, a 3 minus 20x. So now there's only one term right in the middle here that has a dy dx attached to it. Once I have that, I'm going to again move everything that does not have a dy dx over to the right-hand side, which in this case is only this negative y sine of xy. So I'm going to add that over to the right-hand side. And then finally, I now have negative x sine of xy multiplied by dy dx. To get dy dx by itself, I'll divide by negative x sine xy and get this long expression, but that is what dy dx is equal to. Okay, so there's my introduction to implicit differentiation. Try and follow this pattern. Try and follow the examples. Go back, listen to another part, a part of the video again if you have to. Look at the examples again. If you need to, absolutely, please go on, try and research some implicit differentiation if you're still a little bit confused. All right. Otherwise, email me some questions if you have them. I'm going to put just a very few amount of questions on my Malvern along with this video for you to try, not only during this period, but also over the weekend for some homework. Try your best, see how you do, and I will see you in class on Monday. Thanks, guys.